Okay, it's my honor to give a talk to the virtual DLTS user meeting. And my topic is a study of defects in antimony selenium sulfide solar cells by DLTS. Okay. I worked in Department of Electronic Engineering, East China Normal University, which located in Shanghai, China. Okay, first, this is my outlook. First, I will give an introduction of SE solar cells, and then I will give a presample of deep level transient spectroscopy, and then I will introduce the setup of DLTS measurement system, and I will give some results for measurements of defects in Sb2 solar cells by DLTS. So first, I will give an introduction of Sb2 solar cells. Antimony selenium sulfide solar cells is a kind of emerging material recently which have attracted significant research attention and have been employed as absorber in thin film solar cells. It has a one-dimension crystal structure and highly anisotropic properties, which is different from the traditional materials with 3D crystal structures such as CIGS and cadmium tellurium solar cells. The properties of these materials, such as high absorption coefficients and the low band gap energy, which are very close to those of CIGS and CDT solar cells. This makes this material potential absorption layer for solar cells. Further, the abundance, low toxicity and the low cost of antimony, selenide, and the sulfide make these materials potential candidates to replace CIGS and the CDT for the long-term development of highly efficient thin film solar cells. Since the material scarcity of indium, gallium, and the tellurium, and the toxicity of cadmium for CIGS and the CDT will restrict their long-term development for large-scale production in the gigawatt range. There are many measures for growing SE thin film, such as sputtering, closed-spaced sublimation, evaporation, hydrothermal deposition method, and vapor transport deposition. In our lab, we use vapor transport deposition, synthesized as VTD method, to deposit antimony selenium sulfide thin films. Since this method is very simple and low cost. And the process of fabricating the solar cell is as follows. The cadmium sulfide buffer layer was deposited on the ITO glass using chemical-based deposition method. Then the SBSSE film was deposited through VTD method in a tube furnace with 2 heating zones using mixed powders of antimony sulfide and antimony selenide. Finally, patent gold electrodes were deposited on the SBSSE films by thermal evaporation to form solar cell devices. The current efficiency record in our lab is about 8%, and our work has been published in the Journal of Advanced Functional Material. And our other representative publications are listed here. Through about 10 years development, the efficiency of antimony selenosulfide solar cells has exceeded about 10%. However, this is still much lower than the theoretical prediction, which is about 30%. There are many possible reasons may affect the efficiency, in which defects usually play important roles affecting the efficiency. Why we study defects in solar cells? Defects in the forbidden gap of semiconductors usually play recombination centers, which may be bad for the collection of photo-generated carriers, especially for deep level defects, which are close to the mid-gap energy level. The recombination rates will become very high. So the detection and characterization of the properties of defects in the solar cells is very important. Deep level transient spectroscopy, DLTS, is a very useful technique to detect defects in semiconductor devices such as solar cells and LED. By DLTS, the properties of defects such as defect type, defect energy level, defect density, etc. can be obtained. In order to explain DLTS, we must first consider the more basic problem of capacitance transients. This technique is used to obtain information about an impurity level in the depletion region of a Schottky barrier or PN junction by observing the capacitance transient associated with the return to thermal equilibrium of the occupation of the level following an initial non-equilibrium condition. Okay, we will describe the situation in a p-type material in a asymmetric N plus P diode. Figure A is a schematic summary of the emission and capture processes which characterize a particular trap. The capture and the thermal emission rates from the minority carriers, which is electrons in this example, are C1 and E1, respectively. The capture and the thermal emission rates for majority carriers, which is holes here, are C2 and E2, respectively. In the quiescent state of the system, the diode is reverse biased and the observable traps are within the depletion region. So the capture rates are 0 and the occupation of the level is determined by the thermal emission rates E1 and E2. And the steady state electron occupation of a level is described by equation 1. Well, the N1 is the steady state electron occupation of a level, and the big N is the concentration of the trap. We define an electron trap as one which tends to be empty of electrons and thus capable of capturing them. Likewise, a hole trap is one which tends to be full of electrons and thus capable of having a trapped electron recombine with a hole or captured a hole. Then, according to equation 1, an electron trap has to have E1 much greater than E2 and the whole trap with E2 much greater than E1. So this is indicated by the heavy and the light arrows at the bottom at figure C. The emission rates are proportional to the Boltzmann factor and thus depend exponentially on the energy difference between the trap level and the conduction band. And the trap level and the valence band in case of hole emission. Because of this, electron trap tends to be in the upper half of the gap and the hole trap usually in the lower half. As shown in figure B, the capacitance change is caused by using the bias pulse to introduce carriers, and thus change the electron occupation of a trap from the steady state. As this population returns to equilibrium, the capacitance returns to its quiescent value. For the simple linear rate equations 1, the transient is an exponential function of time with a rate constant equal to E1 plus E2. One of these rates usually dominates. Thus, the transient rate for a majority carrier trap is E2, and for a minority carrier trap is E1. The sign of the capacitance change depends on whether the electron occupation of the trap had been increased or decreased by the pulse. An increase in trapped minority carriers causes an increase in the junction capacitance. The capacitance transient due to a minority carrier trap is always positive, and the majority carrier trap is always negative, which is induced by only by majority carriers. Now we consider a majority carrier pulse, which momentarily reduces the diode bias and introduces only majority carriers into the region of observation. The pulse sequence is shown in this figure, and the process is illustrated as follows. First, the N plus P junction is under quiescent reverse DC bias, and the charge is in equilibrium. Then, a filling pulse forward voltage is biased on the junction. During this voltage, the trap will capture electrons from the conduction band. A sudden decrease of junction capacitance would occur. Finally, the reverse bias is restored, and the electrons above the Fermi energy in the trap will slowly released to the conduction band due to thermal excitation, and a slow increase of junction capacitance would occur. Here, we show the capacitance transient induced by a majority carrier trap and a minority carrier trap, respectively. And this is the description of the capacitance for these two conditions. Since the electron emission rate is strongly related to the temperature, so it is visual to observe the different capacitance transients with the help of temperature scanning. As presented in this figure, there are a series of capacitance transients for minority carrier traps at various temperatures. 3 different of time intervals that define something called the rate window are marked with blue, orange, and green respectively. Take the blue marked time interval as an example. As the temperature is scanned, the difference between the capacitance at moment T1 and T2 would change consequently. Meanwhile, this capacitance difference, delta C, will form the relationship curve with the temperature as shown in this figure, which is commonly considered as the basic DLTS output signal S. For the maximum peak, there should be a derivative of the signal equal to 0. The emission rate at this maximum peak height, therefore, can be calculated through the expression for the time constant, like equation 3 shows. It is seen that selection of different rate windows can result in a corresponding change of the emission rate. Each emission rate matches a certain temperature at which the DLTS peak occurs. These points then are made use of plotting an Arrhenius plot as shown in figure C. The approach to obtain this so-named Arrhenius plot is while taking logarithms on both sides of formula 4. So from this formula, by using a semi-log graph of ln En divide T square versus 1 divide T. It is available to extract the two important parameters, including activation energy, and the capture cross-section. That and both of them are applied as characterizing defects. In addition, another variable parameter is the trap concentration NT, which is directly proportional to the DLTS peak height. It is also means that the concentration can be obtained directly from the capacitance change. The simple expression of the trap concentration is given in equation 5, where ND is the concentration of shallow impurities and delta C max is the difference between the immediate capacitance value after the pulse and the stable capacitance value. The DLTS system includes temperature controller, pulse generation, transient capacitance measurement, and finally data processing. The system established in this work used a digital lock-in amplifier MFLI from the Zurich Instruments. The use of this advanced and operationally friendly lock-in amplifier offers wide frequency settings from 1 Hz to 5 MHz. High pulse selection from -10 to 10 volt. Low noise impact and the easy programming controller, etc. Which, okay. The capacitance measured and the pulse trigger are both done by the MFLI lock-in amplifier. The test samples like different solar cells are installed in a vacuum cold well connected to the temperature controller. Ultimately, the control of the equilibrium and the processing of the transient capacitance information is completed through the Python scripts in a computer. Figure B presented the simplified flowchart of this system. The very first and important step is to compensate cables. Cables, which is for accurate impedance measurements. After that, the temperature of the cold well is set through temperature controller. Okay, the temperature setting, however, is not achieved instantly. It required a loop control feature to minimize the fluctuation between the desired temperature set point and the current process temperature, and then to improve the accuracy of the process. The system frequency as well as pulse trigger parameters besides could be convenient set since the MFLI programming interfaces for Python is provided. Here, we further ensure the accuracy of the data through applying multiple pulse triggers. Finally, after obtaining the transient capacitance data, important deep-level defect parameters such as the activation energy, the capture cross-section, and the defect density are obtained by selecting a suitable rate window and a series of data processing. After getting the complete capacitance temperature table to generate the DLTS signals, the time rate window is selected according to the DLTS signals of different samples. The selection of the rate window is related to T2 and T1, and there are generally three selection methods. One, to fixing T1 and change T2. Fixing T1 and change T2. Second, fixing T2 and changing T1. Three, and the third, fixing the ratio of T1 divide T2 and changing T1 and T2. The three methods will bring different DLTS curves. Commonly, method 3 is widely employed, which is by fixing the ratio of T1 and T2, in which case the position of the peak will be shifted, but the size of the peak or trough will not be changed. In this approach, it is much more convenient to find the value of the peak and to analyze the data. Herein, the third method was used in all the study. A number of suitable time rate windows are selected, and the capacitance difference between T1 and T2 is calculated to generate DLTS signals for a continuous temperature at various time rate windows. Since the temperature scan in this study is in 5K steps, the peaks or troughs that appear are refined by Gaussian fitting to the corresponding temperatures. After obtaining the temperature at which the extremes appear in different time rate windows, it can be carried for fitting to obtain the Arrhenius curve, to plot in the Arrhenius curve. And from the slope and the intercept of this curve, the activation energy and the capture cross-section can be derived respectively. And further, the trap concentration NT could also be assessed with the help of equation 5. Okay, this gives some results by using DLTS system to measure the antimony selenium sulfide solar cells. The condition is at frequency of 100 kilohertz with the DC bias sweeping from minus 0.5 to positive 0.5 volt, and with 1 millisecond pulse wide. Figure A presents the transient capacitance of the SBSE solar cell in increments of 5K over a temperature range from 180 to 480 kelvins. It can be viewed that there are slightly changes in the transient capacitance with various temperature in figure A. Since what we need to pay attention to is the recovery process of the capacitance after the pulse. Then the capacitance value after 1 millisecond is zoomed in, as displayed in the inset of figure A, as can be observed that there is a distinct difference in this process over varying temperatures. To achieve the DLTS signal, the blue and the red dashed line are chosen as T1 and T2 respectively to represent the selected rate window. The ratio of the T1 and T2 is fixed as 10, with 5 different T1 from 0.5 to 1.3 millisecond. As depicted in figure B, one obvious peak and one trough are detected, which demonstrate that there are 2 trap defects in the solar cell, and one is a hole trap, and the other is an electron trap. As T1 increases, the peak or trough is left shifted in the range from 340 to 360 kelvins, and from 400 to 420 kelvins. Figure C displays the linear plot through a linear fitting of the 5 points around the DLTS peak or trough. The associated defect energy levels are determined. The defect properties such as trap type, the activation energy level, the capture cross-section, and trap density are concluded in this table. So an electron trap and a hole trap were determined in SBSE solar cells. Then we use the DLTS system to to study the effect of antimony cyanide post-treatment on antimony sulfide thin film solar cells. This data is unpublished data. There are 4 samples here named as sample 1 to sample 4 with different thickness of antimony cyanide deposited on the backside of antimony sulfide. Here we show the results by using DLTS system to study the effect of antimony cyanide post-treatment on antimony sulfide thin film solar cells. So this is unpublished data in our lab. Okay, and there are 4 samples with different thickness of antimony cyanide on the backside of antimony sulfide. Okay, we use DLTS system to measure the spectroscopy and get the linear plot, and we finally get the properties of the defects. Okay, by comparing the defect properties of the 4 samples, we find the defect energy levels of cells S2 to S4 were obvious far away from the mid-gap energy, and S3 owned the lowest defect energy of 0.44, the smallest capture area, and the largest carrier lifetime. So this may explain the highest efficiency of sample 3. Okay, so finally I will give a conclusion of my report. First, antimony selenosulfide solar cells was introduced, which is a new material solar cell. Second, the basic principle of DLTS was introduced. Third, the process of achieving DLTS signal was introduced. And finally, by using the DLTS to studying the SbSe solar cells, we find a hole and an electron trap, and we can get some difference of defect properties for different samples. So this is my publication list. So thanks for listening. And this is the final picture is an image of my university, which is called East China Normal University in Shanghai and China. Okay, thank you.